So it is right at 9:32, and on Tuesday morning, I would have expected students to be here. Maybe some of them are coming, but for right now, there's nobody here. I'll keep the line open, but if nobody shows up, then I won't be lecturing this morning, and I'll just post a video indicating that I will record an actual lecture when students are available for me to lecture to. I wouldn't host a lecture face to face if students weren't there, so I'm not going to host a video lecture if students aren't in class. Good morning, Colin. Glad you could join me this morning. Were you able to click on the link I already put out there, or did you have to use the new link that I just emailed you to get in?
I had to use the new one that you just had sent me.
I'm not sure what's going on there because it's the absolute same link that is in Canvas right now.
It just said link invalid, and then it just redirected me back to the other page.
Okay, well, I went and updated it just to be on the safe side. Um, what I'm gonna do to test it, I'm gonna leave just for a moment, and let me see if it works.
Yes, man. I was having problems
All
with
right.
it too, and
Okay.
then I just turned everything off and got back on.
Okay. So were you able to use the link in Canvas?
Yes, ma'am. At this point,
Okay. Well, then that tells me it's working then because, like I said, it's the exact same link that.
yes, ma'am.
Yeah.
But I had to exit out of everything and turn. I pretty much restarted my computer.
Okay. Okay. Well, I apologize for the technical issues. I imagine that this won't be the last time we have to deal with some kind of technical situation. So I'm recording. I wasn't sure what was going on. I didn't think anybody was going to show up for a moment there. So I'm really glad that y'all managed to get in. I'm going to go ahead and share my screen. Okay. Uh, Bear with me because I was looking at the link to make sure that it was working right. Okay. So what I've worked on was posting the videos for our meetings in a different way so that permission issues wouldn't be continue to be a problem. Some students were saying they couldn't get into the videos for whatever reason. I never was able to get a real definitive answer from IT. Even when I went in and changed the permissions, some students were saying they were still having trouble. So what I did was just download the videos. And I went back this weekend and I uploaded all the videos from our class meetings, and I put it in the announcements, and as well as right in the weekly overview. So if you're having difficulty, you can just click right within Canvas and watch the video. You don't have to worry about watching the video through Teams. Now, of course, you have to be using Teams to get into our class sessions, but you don't need Teams to watch the videos anymore in the event, you miss the class, or you're running late or what have you. I will say this: if it ever turns out in one morning that we don't have anybody in class, I'm probably not going to record a lecture then, because I mean, if nobody was in class face to face, I wouldn't do it. So just to be aware. But again, I'm glad you guys made it in, because I was starting to worry about what was going on. All right. So this week, if you've looked at the weekly overviews, we're dealing with thermodynamics. Don't forget that your responses to the application activity are due this Saturday. Again, you do not email me application activities. Problem sets get emailed. Application activities get completed in the discussion forum. Hit the reply button, post your answers, and if it tells you to respond to classmates, do so. But do not email me your application activities, because I will just email you back saying, put this in the discussion forum. And if you don't, then you get a 0. So just be mindful of that. I mean, I'm still getting students emailing me their application activity practices. And that shouldn't be happening, because information's been out there for several weeks now that you need to put those in the forum. All right. So with that being said, I can go ahead and get into the lecture notes. So what I'm going to do today is to cover the information on temperature and heat. And then on Thursday, I will work some examples regarding heat, and then cover the information on thermodynamics. So this packet deals with the idea of temperature. And so they start off by, once again, emphasizing the difference between the everyday conversation use of the word temperature versus the physics or scientific definition of temperature. And a lot of times, hello?
Sorry to interrupt you, but I can't see your screen sharing right now.
Okay, let me stop screen sharing. Well, okay. Let me see if I share it again. That better?
Yeah, now it's working.
Okay. I think some of you were waiting in the lobby, and so you hadn't formally been admitted. Maybe that's why you couldn't see it. I'm not sure. But so this this packet is dealing with temperature, as I mentioned, and it's emphasizing the notion of qualitative language that we use sometimes to mean temperature, that is really not grounded as in science as far as the physics definition of temperature. So a lot of times we use the words like hot or cold to mean temperature, but hot or cold doesn't necessarily mean temperature, because we can interpret hot and cold differently. So, I may be in a room and find that room cold and you may be in the same room and you find a room hot, that doesn't quantitatively tell us about temperature. But when we want to quantify temperature, we measure it. And we measure it using thermometers of some sort. And we utilize scales to measure temperature that I'll show in a moment. And the reason we want to be able to do that, because of course, you know, physical science is based on measurement. And the whole idea is that these measurements have to be reproducible. So to help with that whole measurement process, there are various temperature scales that we use. Now, in this country, we know we use Fahrenheit on a regular basis. If you turn on the news report and they talk about the temperature today, they're going to talk about using Fahrenheit measurements. Well, for a lot of basic everyday scientific measurements, we do use a different scale called the Celsius scale. Now, the Fahrenheit scale and the Celsius scale can be used to measure temperature, and they are both based on the boiling point and freezing point of water. So on a Fahrenheit scale, 32 degrees Fahrenheit is freezing for water, and 212 degrees is boiling for water. But on the Celsius scale, the numbers are a little different. 0 degrees Celsius is freezing, and 100 degrees Celsius is boiling. And so we can get away with the Celsius and Fahrenheit scales for most things. But the issue with them is that because they depend on the boiling point and freezing point of water, those values change as we change the atmospheric pressure. So for example, if you're in Mile High City, Colorado, then the water is going to boil, but it's going to boil at a temperature that's less than 212 degrees Fahrenheit or 100 degrees Celsius. So the water will boil, but it will be cooler. And that is because of the difference in the atmospheric pressure in Colorado versus, for example, Louisiana. Well, that presents a problem if you're trying to do, you know, precise quantitative measurements regarding temperature. And so we turn to a scale that does not suffer from this dependence on atmospheric pressure. And that is the metric system scale, the Kelvin scale. And so when we measure temperature in kelvins, we don't say degrees Kelvin, just Kelvin, then we don't have to worry about that issue with the boiling point and freezing point changing. We call the Kelvin scale the absolute temperature scale, and that is because on the Kelvin scale, we can define a temperature called the absolute zero, and that is 0 Kelvin. And that's the lowest temperature possible. And we'll see here momentarily, this absolute zero is the temperature at which all molecular motion cease. In other words, the substance has 0 energy when we are at absolute 0 on the Kelvin scale. And so on the Kelvin scale, the freezing point and boiling points are 273.15 Kelvin and 373.15 Kelvin respectively. Now, if you look at this closely, you see between the freezing point and boiling point, there's 100 Kelvin. That's the difference. And if you look at the Celsius scale, there's also 100 degrees difference. In that case, the difference between freezing and boiling on the Celsius scale is 100 degrees Celsius. And so because the difference between freezing and boiling on both scales is 100, we can utilize the idea that the change in temperature is the same. I didn't say the temperature was the same. I said the temperature difference is the same on a Celsius and Kelvin scale. So they're doing a comparison there, just to kind of give you a visual of a comparison between the Celsius and Kelvin temperature scales. It says, so on the right side, it shows that the Kelvins and degrees Celsius have the same magnitude, and that's what I was alluding to. The temperature difference is the same on either scale. And then you can see where the zero falls, and then you can see that we get down to here, the absolute zero, and that equates to negative 273.15 degrees Celsius. They show here the notion of some temperature measurements in Kelvin for natural phenomena, things that happen in our environment, in our physical environment. And you can see that a lot of those things reference the behavior of stars. And we can see that within a fairly small range or some everyday phenomena that we deal with, like water boiling, freezing, even liquid nitrogen. That's something that we are, we have experienced kind of on a more everyday basis, as opposed to, for example, the interior of a neutron star. I mean, we don't deal with that every day, but things like water boiling and freezing, which happen within a very small range on the Kelvin scale, are some natural phenomena that we measure and deal with regularly. There are different types of thermometers, and that's all I'm gonna say about that. We don't need to get into the different types and how they work and all of that. I mentioned the idea of absolute zero, and this absolute zero interest, if you will, or concept, comes from studying gases. And so when you look at the relationship between the pressure, the volume, and the temperature of gases, there's a relationship. And so when we look at gases and we start to make certain measurements, it was noticed that when we extrapolate the temperature to zero, it always came up to this negative 273.15 degrees Celsius. And that kind of led scientists to think that, hey, that's probably that's the lowest temperature that we can get, because no matter what gas, when we look at its behavior, when we analyze, when we visualize its behavior on a graph, for example, we notice that all the values point toward this same direction, this negative 273.15 degrees Celsius, and they call that absolute zero. And so that is the lowest temperature possible, and it is also the temperature at which all molecular motion cease. Well, if nothing's moving, there's no energy. So we have to, well, there are gases that come close to that behavior, but absolute zero, much like objects moving at the speed of light, that's a theoretical construct, if you will. Okay. And this is really, this idea of absolute zero is really only practical when we talk about like ideal gases, for example. this idea of the zeroth law of thermodynamics, we'll come back to that on Thursday. We'll talk about thermodynamics more then. I'm not interested so much in the linear expansion and thermal expansion of materials that in this course. We won't really deal with that. Ideal gases, I've just mentioned that, again, ideal gases allow this notion or concept of an ideal gas allows us to simplify our analysis of the behavior of actual gases. And so they found that there's a consistent relationship between pressure, volume, and temperature for ideal gases. And I'm not going to spend too much time on that because if you are in P-Tech, you're going to get exposed to this a whole lot more. This idea of the behavior of gases and Charles' law and Boyle's law, you'll be exposed to that. And then Avogadro's number in moles, I'm not going to go into that either. And I'll say also, I'm not going to focus too much on these areas because those are also something that you cover in chemistry. And, you know, I try to leave the chemistry portion to the chemistry instructors to cover with you. And so this idea of these phase diagrams and the relationship between pressure, volume, and temperature, Dalton's law, Charles' law, all those things, you'll get to those in chemistry class. Okay, oh, let me admit this. See about sharing my screen again. Why is it doing that? Okay. Bear with me for a second. Yeah, something's going on here with my shared window. Let me see what's going on there. Okay. Now, let me see. Hold on. Just bear with me because it's not doing what I thought. Oh, that's why, because I shut down Canvas accidentally. So let me reopen Canvas here. Get back into my presentation. Sorry for that. I'm hitting the wrong buttons this morning. Okay. Here we go. Thermodynamics and okay. Now let's see if I share now. There we go. Now back into it. Sorry about that. Okay. So again, a lot of this information on the behavior of gases and what have you, you'll deal with that in some of your other classes like chemistry and some of your P-Tech classes. So what I want to do now is I want to go ahead and look at information on heat. Like I said, I'm presenting some background information today, and then on Thursday, I'm going to use that to solve problems that deal with temperature and heat, and then discuss thermodynamics with you on Thursday. So we have to be careful, again, to distinguish everyday conversation from physics conversation. And so a lot of times we use the words heat and temperature to mean the same thing, but they do not, because heat involves energy transfer because of a temperature difference. So they aren't the same thing. And so it says here, for example, the temperature of an object is a measure of the average kinetic energy of its atoms and molecules. And we just talked about we can measure temperature on several different scales. Temperature is a quantitative way to tell us how energetic, how much kinetic energy the molecules of a substance have. So if, we know how to measure temperature, but what is it? It is a measurement of the average kinetic energy of the atoms and molecules in a substance. Heat, on the other hand, represents the thermal energy of an object. You can think of thermal energy as total energy. So we know that there are different types of energy, kinetic and potential energy, and thermal energy encompasses both of those, whereas temperature only focuses on kinetic energy. So they're not the same. Okay? And temperature tells us how much kinetic energy the molecules have, but it doesn't necessarily imply energy exchange or transfer of energy, whereas heat does. And notice in the definition of heat, it says it's a spontaneous transfer. That means it happens all on its own. You don't have to do anything to make heat go from a hot object to a cold object. That happens naturally. And we'll see this again, this notion of a natural process when we talk about thermodynamics on Thursday. And so they give the analogy. Let's say you have a glass full of water and a swimming pool full of water. They can both be at the same temperature. The water in the glass and the water in the pool can both be at the same temperature, but they are not going to have the same amount of heat because you have more mass of water in the swimming pool is going to have more heat. And so we see that in this way, heat depends on, not only on the temperature of a material, but the amount that you have of it and the type of material that you have. And so we'll see that here played out later on in our investigation of a property called specific heat capacity. The equivalence of heat and mechanical work. So we talked last week about work and energy, and we talked about the idea of mechanical energy being kinetic energy and potential energy. The primary idea here is that mechanical work involves some type of transfer of energy because of motion. And so heat and this work are kind of interchangeable because heat in some ways, just like work, involves a transfer of energy. And so that's what they're alluding to here on this particular slide, in that we can convert heat and work from one to the other. They're interchangeable. And so if you've ever been, for example, in a science museum where you pedal the bike, and as you pedal the bike, there's a set of paddles in this big container of water, and you can observe the temperature of that water change as a reflection of the fact that it's heating up from the mechanical motion of paddling the bike. The mechanical work that you're doing on the bike is transferred to the water in the form of heat. And so we define this, the amount of mechanical work that's needed to produce heat is called the mechanical equivalent of heat. So you can convert mechanical motion energy, mechanical work, into heat energy. And so there are units that we use for heat. The one we're most interested in is the metric system unit. That's joules. Calories, we use that a lot of times when we're dealing with food, or we want to specifically refer to the mechanical equivalence of work and heat. We use calories in some ways to do that. In other words, how many calories do you burn if you ride the bike? So we're equating the work with heat, and calories is used most often for that purpose. But for our purposes, we focus on the metric system, we're going to use joules. So last week we learned about kinetic energy and potential energy and work, and they all are measured in joules. And here now this week we're learning about heat, and it is also measured in joules. And that's how we know they're equivalent, because they're using the same units, and that is because they're interchangeable. All right, give me just a moment. Give me about 5 minutes. I'll be right back. All right, thanks for your patience. Again, I'm working from home just like many of you, and sometimes I gotta attend to some home stuff while I'm trying to teach. So thanks for indulging me. All right, so now that we have some background in this idea of temperature and the various scales that we use to measure temperature, and an understanding of what heat is, energy basically, energy in motion. So we can now look at the relationship between temperature and heat. So it tells you here that if we put two substances that are at different temperatures in contact, heat will naturally transfer from the hotter object to the colder object. And the amount of heat that's transferred depends on how big that temperature difference is, the amount of the substance that you have, and this property, specific heat capacity. And so different materials will behave differently and transfer different amounts of heat because of this specific heat property. This specific heat is material dependent. different materials have different values of specific heat. And so when we are looking at this notion of specific heat, we see that some materials have a fairly small specific heat, and some materials have a very large specific heat. And what that tells us is how easy or how difficult it is to heat up or cool down the material. So when we transfer heat into the material, we raise its temperature and heat it up. And when we remove heat from a material, we drop its temperature and cool it down. And these values of specific heat tell us how easy or how difficult it is to do that. And so for those materials with a very small specific heat value, it is very easy to heat it up and cool it down. But for those substances that have large values of specific heat, and water is not even shown on this table, it has the largest value of specific heat, 4,184 joules per kilogram degree Celsius. Which tells us that water is a very heat intensive material, just like they're showing the human body there. Well, the human body is mostly water. So it makes sense that it has a high specific heat value. And that means that substances with a large specific heat are very energy intensive if you want to heat it up or raise its temperature, but they also retain the heat much more readily. And so once you heat them up, it takes more time for them to cool down. So again, these specific heat values are material dependent. You look them up in tables, just much like the table that's provided, and then you use it in this formula. So in this formula, Q is the amount of heat transferred in or out. If you're putting heat in, Q is going to be positive. If you're taking heat out, Q is going to be negative. And so M is the mass in kilograms. So you're looking at the final temperature and your starting temperature, delta T. And this is why I was being very specific about the idea that the temperature difference is the same on the Celsius and Kelvin scales, because when we use delta T in this formula, we can use degrees Celsius or Kelvin, because delta T is the same, not T, delta T. There are also heat exchanges when there is no temperature change. So when a material is undergoing a phase transition, and there are three phases of matter that we care about: solid, liquid, gas. When a substance is transitioning from one phase to another, we have to either put heat in or take it out. But here's the issue: when you are putting heat in or taking heat out to change the phase, the temperature stays constant. And if we look at this formula, if the temperature stays constant, delta T is 0, that means our Q is going to be 0. Well, we know for sure that it makes no sense to say that we can boil water, for example. That's a phase transition. We can boil water without putting in any heat. This formula says Q is 0 if delta T is 0. But we know from experience that it takes heat to melt ice, for example, or boil water, or we have to remove heat if we want to take the liquid water and turn it into ice. So we can't use the specific heat formula whenever a substance is undergoing a phase transition, because delta T, the change in temperature, is 0. So we have to go to a different formula. And this is called the latent heat formula. And this formula allows us to figure out the amount of heat released or absorbed during a phase change. Now, in this formula, M is the mass, and L is called the latent heat coefficient. I always say the latent heat constant. And we'll see when I solve problems on Thursday that this L can have different values, and that's what they're alluding to here. When you use the latent heat formula, you have to know what phase transition is taking place, because the latent heat values depend on, are you doing a phase transition around the freezing point or the vapor point, the boiling point. And so L has two different values, LF and LV. The LF value is for freezing point transitions, and the LV is for vaporization phase transitions. And so that's what this graph is showing. For example, when you're here where ice is either melting or freezing, while that is happening and the temperature is staying fixed at 0 degrees Celsius, then you are not going to have a temperature change. And so since we're at the freezing point, we need to use our LF value, and I'll expand on that more on Thursday. Similarly here, if you're undergoing a phase transition around the boiling point of water, where you could either be vaporizing or condensing water, and the temperature is going to stay fixed, so you would have to use the LV value of the latent heat coefficient. So we'll see that on Thursday when I solve an example problem for you, utilizing this idea of heat transfer with a temperature change and heat transfer with a phase change. You can only do one or the other. You can't do both at the same time. And so we'll see on Thursday how we have to break down our our heat exchange processes in steps to figure out how much heat we would need to accomplish taking a material from one starting temperature to another. So how do we actually transfer the heat? We actually transfer the heat using 3 processes: conduction, convection, and radiation. So let's look more closely at those. Conduction is a heat transfer between objects that are in direct contact. I always say conduction is heat transfer by way of touching. So when things touch each other, you can have heat transfer taking place, and that happens spontaneously from hot to cold. Heat naturally flows from a hot object to a cold object when they're in contact with each other. We're not going to get into the heat transfer rate and thermal conductivity, but just know that the temperature difference between the hot object and the cold object will influence how fast the heat is transferred. And different materials have different conductivities. Notice, just like different materials have different density, just like different materials have different specific heat values, different materials have different conductivity. And so you can see on this chart here that materials with a very low value for thermal conductivity are insulators, basically. They don't conduct heat very well. For example, like styrofoam, you can see it has a really small value of thermal conductivity, and that's why styrofoam is used many times as the material in a thermos bottle to minimize heat transfers. If you cut open a thermos bottle, you will see a layer of styrofoam. Ice chests are made of styrofoam for the same reason, because they minimize the amount of heat that's being transferred. But materials like silver, for example, that have a high thermal conductivity means they conduct heat very easily. It would be, really great if we had, uh, you know, uh, silver wires for, like, for example, for electrical purposes, because silver is an excellent conductor. The problem is that it's very expensive, and so we go to a material that has a high conductivity, but it costs a whole lot less, and that's copper. So if you look at your electrical wires and things like that, you'll see that they have, a copper strip inside, and that is because copper is an excellent conductor and is a whole lot cheaper than silver. And they look at thermal conduction at the microscopic level. We're not interested in the microscopic behavior of materials at this level. So the next method of heat transfer, notice that what we're looking at is we can figure out how much heat using our Q formulas, either with a temperature change or a phase change. But the question is, how do we move the heat from one place to the other? Conduction is one way. Another way is convection. And I always say that convection is heat transfer by way of fluid flow. So you're either moving warm or cool air, or you're moving a warm or cool liquid. And as those warm or cool fluids circulate, they either give off heat or absorb heat. Okay, they give the example of a radiator in the car. You put this antifreeze in your radiator, and there's a fan that drives that coolant through your system. And what it does, it absorbs heat out of the system and releases it, keeping the engine at a cool or reasonable temperature. My favorite example of convection is a convection oven. You can use a convection oven to circulate warm air and cook food evenly. And so they give the idea here of a pot where you have these natural convection currents in water as you are heating it up or boiling it. The last method of heat transfer is the thermal radiation. You can think of this as heat transfer by way of light. And light can come in many forms. We're most familiar with visible light, white light, if you will. But there are other forms of light that are invisible, like infrared, ultraviolet, X-rays, gamma rays, microwaves, radio waves. Those are all forms of light. And so this light or thermal radiation can transfer heat. And our most obvious example is the sun. That's exactly what the sun is doing for us. It gives off radiation in the form of different wavelengths of light on the electromagnetic spectrum, from visible to ultraviolet and infrared and what have you. And some of those light radiation energy, some of it is very helpful because it facilitates things like photosynthesis, but then some of that radiation from the sun is very damaging, for example, causing things like skin cancers. We're not going to look at in any detail this rate of heat transfer for thermal radiation or this emissivity. We're not going to focus on that too much here in this course. So Again, what we've looked at today is what is temperature? How do we measure temperature? What is heat? We look at heat when you heat transfer when you want to change the temperature of a substance, and heat transfer when you want to change the phase of a substance. And I'll work examples on that on Thursday. And then we looked at methods of heat transfer: conduction, convection, radiation. So on Thursday, I will solve some problems that deal with heat and temperature, and then we'll talk about thermodynamics. So with that, I am done with my part. I'm going to stop the screen share and ask if there are any questions. If you have questions, just unmute your mic and ask. I will post this recording as soon as the system generates a link for me. You'll be able to find this recording in the announcements and in the weekly overviews. So I'm open for questions.
Yeah, Dr. Z.
Yeah.
On the lab report, whenever we're doing the second one for this week, the skater one,
Yeah.
whenever we're recording our data, you wanted us to record just the left side of the
Yep.
curve
Yep.
for both data tables.
Yep.
All right, that was it. Thank you.
Mm-hmm. So if you don't have any questions for me, we're done. Um, Again, I will post the recording here as soon as I get a link from the system for the recording. Hunter, do you have a specific question for me? Hunter, Mr. Forbes, do you have a question for me?